So let's look at radiation, which is one of the ways a human can lose heat. You're probably familiar with the idea that most everything glows at some level. Let's look at the physics behind this. Let's imagine we've got some matter next to a bit of empty space. Now, empty space isn't really empty, it's full of electric and magnetic fields. And the matter isn't really solid, it's made of atoms that are vibrating around because of their heat, or jiggling backwards and forwards. Now, it so happens that this jiggling of the atoms and the electric and magnetic fields can influence each other. If you think about it, there's an electric field that will pull on any charges here. It'll pull, if there's an electric field pointing this way, it'll pull the electrons one way and the protons the other way. And that could cause any free electrons to jiggle around, it could stretch atoms, and generally make them vibrate. The reverse is also true. Let's say you have an atom that's moving backwards and forwards, especially if it's a polar atom, so it's got a displaced charge or it's been ionized, that will generate, as it moves, a jiggling electric and magnetic field. Okay, so it is possible to have matter next to empty space where that matter is affecting the electric and magnetic fields in the empty space, so the electric and magnetic fields are affecting the matter. Now let's think thermodynamics again. You remember the principle of equipartition? This was the idea that if something's in thermal equilibrium, so everything's interacting very strongly with everything else, then every form of random motion will have about the same amount of energy. So if you remember, we said that the horizontal jiggles will have the same energy as the vertical jiggles, the vibrations of particles on springs will have the same energy as the rotation, and so on. Now, if the interaction between the matter and the empty space electric and magnetic fields is strong enough, then the same thing will apply. You've got an energy of 1/2 kT for every type of vibration and motion of the atoms, and that will also go into every type of vibration and motion in the electric and magnetic fields. Brilliant idea. And if we run with that idea, you are therefore able to calculate what electric and magnetic fields there must be close to a lump of material at a given temperature. It'll be whatever has this 1/2 kT of energy in every possible form of jiggling and vibration. We won't do that calculation here, you'll see it in second year thermodynamics, but the net result is what's called black body radiation. Why is it called black body? Well, we're making the assumption that the jiggles of the matter and the jiggles of the electric and magnetic fields are very closely coupled, each affects the other. What that means is any radiation that comes in will transfer its energy to the jiggling of the atoms. So the surface will appear black. That's because any radiation that lands on it is being absorbed. On the other hand, it also means any jiggling of the atoms will transfer its energy to the radiation, so it means it will also radiate very strongly. Now, if something is a black body, so there's this perfect coupling between the electric and magnetic fields and the jiggling of the atoms, then something will radiate according to the Stefan-Boltzmann equation. Radiated power per unit area, or total power, is equal to the area times a constant sigma, a sigma t to the 4th, where sigma is called the Stefan-Boltzmann constant and is equal to 5.67 by 10 to the minus 8 watts per meter squared per Kelvin to the 4th power. So that's called the Stefan-Boltzmann equation. So this will tell you how much something that, if it's a perfect black body, will radiate. It depends crucially on the temperature and also on the area. Clearly a bigger area means more radiation. What wavelengths does it radiate at? Well, that's given by the Wien displacement law. It tells you that the wavelength of the peak emission, it's spread over a range of wavelengths, but this is the peak, is equal to B, which is a constant, over the temperature, where B is 2.9 by 10 to the minus 3 meter Kelvin. Now, for a human body, for example, we're at a temperature of about 36 centigrade, which is 273 plus 36 Kelvin, which gives us a wavelength of about 9 by 10 to the minus 6 meters, or 9 micrometers in the mid-infrared. So that means the human body is radiating at mid-infrared wavelengths. If something is much hotter, like the surface of the sun at about 6,000 degrees, then the wavelength would be shorter, and indeed the sun emits most of its heat as yellow visible light at about half a micron, whereas something hotter still, like a quasar, would emit in the ultraviolet or even the X-rays. But now, this is all assuming that an object is a perfect black body. Is that actually true? Well, the way we normally handle that is by adding an emissivity to the equation. So instead of saying P equals A sigma T to the fourth, we say P equals emissivity A sigma T to the fourth, where this emissivity is a fudge factor. That tells you how close you are being to being a perfect black body. Now, I should warn you, emissivity may be a function of wavelength. It might be higher at some wavelengths than others, but we can treat it just as a single number for the moment. Now, something that's very polished may have an emissivity of 0.01 or something like that for a mirror, but even a very polished mirror is seldom less than 2 or 3%. For most objects, emissivity is about 0.5 up to 1. For example, for human skin, at infrared wavelengths, the emissivity is about 0.93. That's actually both for white-skinned and dark-skinned people. It turns out at infrared wavelengths, we all have dark skin. All of us are black. At visible light, it's a bit different. The emissivity of white human skin is about 0.4, whereas it's about 0.8 for the dark skin. But given that humans actually mostly radiate out at the infrared, that's irrelevant. So normally for ninja purposes, you can treat the emissivity as a half or 1 or something like that and not worry about it anymore.